I'll start the talk by briefly reviewing what a variational autoencoder is and why do we even want to do autoencoding, and then I will try to explain a structured type of a variational autoencoder in quite some detail, and only after that I'll start talking about my contribution. So please feel free to interrupt me, because the goal of the talk is to sort of make you familiar with how to introduce structured in variational autoencoders and what benefits might bring for learning representations. So let's start with what is a variational autoencoder or an autoencoder in general. So introduced by two works in parallel by Kingma and Resende, 2014. A variational autoencoder is a type of autoencoder. So imagine you have an input, which might be an image or might be a different modality, and you have some encoder, which is typically a neural network. You create some sort of representation from that, here depicted by a Z. Then you have a decoder that takes that Z and reconstructs the original image, right? So we do this because it's a type of unsupervised learning, which means we don't need any human-generated labels, and it allows us to train models that can extract some useful type of representation that we can use in downstream tasks. So in a variational autoencoder, this whole setup is made probabilistic. So more formally, let's say we have some input X, and our encoder really provides a probability distribution, Q of Z given X, with some encoder parameters here denoted by phi. Then we have some stochastic encoding. This encoding is stochastic. Z is really a random variable that we sample from Q, and Q is, in a typical setup, just a Gaussian distribution parameterized by some parameters predicted by a neural net. Then we have a decoder, which is again probabilistic, so we just have a conditional probability distribution of X given Z with some parameters theta, and we can sample from it an approximate reconstructions of our input. So far, so good. So to train a variational autoencoder, what we really want to do is we want to learn the marginal distribution of the data here given as P of X with some parameters. So we don't really know what the distribution is, right? So that's why we use what's called a latent variable model, which means that we introduce a latent variable here Z, and we have this, conditional distribution times a prior distribution, and we integrate out the latent variable. So you can think about it as a type of a infinite mixture model. I hope everyone's familiar with a Gaussian mixture model. So what it corresponds to, imagine that you have P of X given Z for a particular instantiation of Z can be thought as, for example, a Gaussian mixture. And then you take one mixture like that for every possible Z, and you basically paint your target distribution, getting a sort of an infinite mixture model, which can model a arbitrarily complicated distribution over X, for example, over images here. So to train a variational encoder, we want to maximize the marginal log likelihood, and we typically lower bound it by a quantity that is always lower or equal, called an elbow. I will not derive it, just to give you an idea how this looks like. This is a fairly complicated expression, but all I want you to know here is that we have one term that corresponds to some reconstruction error, so you want to reconstruct the data, and there's a second term that is some kind of a regularization. Does this make sense so far? Good. So especially in the second term, in the regularization, we have this conditional distribution Q of Z given X, which is our approximate posterior, and we have the prior distribution P of Z. So this is important because having this term in our objective will bring the approximate posterior, which allows us to do some inference from data very close to the prior. Now that means that in the absence of the data, we can just sample latent variables from the prior and generate new data. So for now, it's pretty inconsequential, but I will show you some examples later where it is actually useful. So this was just a very quick recap on a variational autoencoder. What I would like to tell you about now is the model called Attend Repeat, or AIR for short, which was introduced by Ali Eslami and others in 2016. So I hope the video works. Yeah, it does. So what AIR does is that it's a type of a structured variational autoencoder which can learn to decompose an image into separate objects. So what it does, it scans the image iteratively, and every time it looks at the image, it picks a region that it encodes into a separate latent variable, and then it reconstructs the image by starting with a blank canvas and painting one object at a time. So it does a few things. First of all, it can infer the number of objects in the image, and then it can describe every object with a separate latent variable. It's very cool in the sense that it allows us to do unsupervised object detection. However, if you wanted to apply it to videos, to image sequences, then that means that even though we can detect objects in separate frames, there is no way to tell that, hey, this pair of latent variables corresponds to the same object. So there is no way of drawing correspondences between objects. So what we would like to have is something like this. So in the top row, we have input sequences of moving digits. In the bottom row, we have reconstructed sequences with marked bounding boxes. So we would like to be able to have a model that can extract variables for every object and that could link those objects between frames, thereby doing both detection and tracking. Are there any questions up to this point? Right. Not really, no. Not really, no. So this is a very this works only with very simple setups. So in particular, in those types of models, there's nothing that actually explains backgrounds. It works whenever we have things without backgrounds, which is actually a pretty large classes of inputs, because whenever you have a static camera, which means the camera is in a single place and the background doesn't really change, you can just extract this background in a simple pre-processing step and then still do detection tracking, and I'll give an example for real data like that. Any other questions? Okay. So this is our extension to the model. But first, let's start by talking about AIR and how it actually works and why it works. So in AIR, in Attentive Repeat, every object is explained by a separate latent variable, but actually there are several types of latent variables. So first of all, we have a variable what, which describes the appearance of an object. We have where, which tells us about the object position and its size. And we also have a binary presence variable, which tells us whether the object exists. So if we already have a variable for this object, we don't really need the presence, but the presence variable is just useful to perform inference. And I will explain why. So let's have a look at the generative model. Who's familiar with graphical models? Okay, not a lot of people. So let's just say that so the nodes here, so the circles in my presentation corresponds to random variables. So basically variables drawn from some probability distribution. And we talk about the generative model. It's a model that does not have any access to the data. So basically, it's some prior distribution that we might train by training it on the data, but when we generate this data, it doesn't really have access. So I'll show an example later where having a prior distribution like that allows us to actually predict the future. But for now, this is basically about specifying a process which gives rise to our data, that generates our data, and this allows later to do inference from the data. So basically, this is a mechanism that uses latent variables and translates it to the data, and later we'll be able to specify a mechanism that, given an image, produces the latent variables that we care about. Does this make sense? So here, we will, to generate data, first we will sample a number of objects from an image. So from some probability distribution, we could use a geometrical distribution or maybe a categorical distribution or something similar. Then, so we have those three different latent variables, right? So a number of objects is one of them. And then we have where, which is the location and scale for every object, and we have what, which is the appearance of every object. And we'll just sample them from standard normal distributions, so basically multivariate Gaussian distributions centered on 0 and 1. And then we will pass all the variables that we have for a decoder, and we'll recreate the image. So let's look at how does the decoder work. In this case, if you take the what component for every variable, you can pass it through some neural network and ask that neural network to reconstruct a small image of the object of interest. Once you have that, you can use the where variable to transform this small reconstructed object, or an attention glimpse, as it is often called, and place it onto a bigger canvas, like shown here. So this transformation, if in this particular example, is done by what's called a spatial transformer, which is a model introduced by Jaderberg and others in 2015. And it basically takes the small glimpse and places it onto a larger canvas. And finally, we can just add those canvases corresponding to different objects together to create the final image.
You mentioned Gaussian distribution, right?
Correct.
Because I thought that what is something discrete, like a number, or can you?
Sure. So here we have digits, right? So you could think that what would correspond just to a class of that image, so basically what number it is, right? But what you really care is the appearance. So like the class itself does, so if we were talking about 100 in digits, a class tells you about the general shape, but doesn't give you the concrete appearance of that, right? It doesn't give you all the details. So here we model what as basically as a vector of real numbers that we sample from a Gaussian distribution. In terms of a prior, in just normal 0, 1. In terms of the inference, it's a Gaussian whose parameter is predicted by a neural net. Does that answer your question? No.
So we have a vector of numbers.
Correct.
Okay, and then from these numbers we get to a digit. In what way?
Right. So the digit is just an image. Right? So you have some vector of numbers that describes this image. This is some representation for that image. And you have a neural net that takes this vector and produces some bigger vector that you can reshape into a square.
Okay, yep.
Right? And that square will contain the digit, hopefully. I mean, the model is trained to minimize reconstruction error effectively. That's why it learns to produce those digits. Does that answer your question? Cool. Any other questions at this point?
So what is this ST?
ST corresponds to a spatial transformer. This is, I won't talk about detail in this, but you can basically think that ST just takes the GT, which is the small glimpse, and performs some kind of affine transform. So basically shift and scale, and maybe shear or rotation or something like that, where parameters of that. I had a timer instead of stopwatch, sorry. Yeah, I do that sometimes. Right, so ST is an affine transform, and the where variable is just parameters of an affine transformation. Does that make sense?
Yeah, just wondering if ZT where is just Gaussian, how does it transform? Well, if you just plug it into an affine transform, or what?
So there is some nonlinear mapping, some layered nonlinear mapping between the Gaussian and the affine transform, that given the real numbers sampled from a Gaussian learns to give you parameters of an affine transform, which is basically size and position and rotation and so on. Does that make sense? Any other questions?
Is this transformation really required to include that use this where doesn't encode some unreal position data, right? So this is just some latent variable, right?
So it wouldn't if you didn't have the spatial transformer, right? If you didn't use a spatial transformer, it would just be a latent variable that would allow you to reconstruct the image in some sense, right? But because we're using the spatial transformer, because we're putting this additional structure into the decoder, it forces this latent variable to have a specific meaning, which corresponds to size and position. That's why in the video that I showed you before, we could draw a bounding box, right? So that's why we know where the object actually is in the image, and without having this, we wouldn't be able to do that. Correct?
Right?
Mm-hmm.
And then you have to define the where, or you can define the what, or am I getting something wrong?
That's correct, yes.
Okay.
Yeah, so that's for inference, whereas here the generative model treats where and what independently. So basically, if you just want to generate an image with a bunch of objects, you say, hey, I'll sample a bunch of location, I'll sample a bunch of corresponding appearances without actually conditioning a location, and I'll put them in an image. So this is just for like generating new data. This is just for sort of defining the process that generates the data. However, if you want to do inference, the inference is in fact done as you say. So first we figure out if an object exists, then where it is located, and only after that how it looks like. So it is a different order. Another question. What do you mean? So yes. So we assume we don't know this, right? So we would like to learn this, and so yes. So here in this setup we need a probability distribution over everything that we're learning. And it's so if you want to have a probability distribution over parameters of an affine transformation, you would have to define a probability distribution over the SO3 class, for which is like the mathematical space in which those parameters live in. And like I'm sure it's possible, but me personally, I don't know how to define a probability distribution over that. So it's just easier in that sense to define a Gaussian and let it be transformed somehow, and the system can learn how to do that. Okay, cool. Let's move on. So that was the generative model, but now we're interested how to actually figure out what are the latent variables that describe any given image, right? So if we get an image X, we would like to figure out what are the different variables Z and how many there are. So basically, we would like to count the objects and describe them. And this is done by this sequential inference procedure. So now you can figure out that so X here is an image, and we'll be using some kind of a recurrent neural network with a hidden state H. This neural network will look at the image iteratively and will produce a latent variable at a time. So Z here is again presence, location, and appearance of the object. And then it will look again at the image and will take into account the previously generated object, and will try to generate another object. So we're inferring one object at a time. We again have a binary presence variable. And inference stops when this presence is 0. So for example, if we look at this diagram again, for the first object, the presence was 1. For the second object, the presence was 1 again, and for the third object, the presence was 0, therefore we decide to stop inference, right? So using this iterative scheme, we can figure out how many objects there are in the image. Once we have this, we can take all the variables that we have, so number 1 and number 2 in this case, and just pass it to the decoder to recreate that image. So to put together the whole model looks fairly complicated like this. This is the encoder and the decoder, which is sort of, there's much more structure than like a vanilla off-the-shelf variational autoencoder, but because of that, we have a variable number of latent variables for every image, and we have some specific meaning for every variable that we create. So you can also ask why it actually works, so why it even decomposes an image into separate parts, which can be unclear if you just look at this model. And there are 3 things. So first of all, the prior on the number of objects that we have encourages a low number of objects. So in the original work, they used a geometrical distribution, which basically means that the probability for increasing number of objects decreases exponentially. And what that means in the terms of the objective being optimized is that you pay a penalty for generating more objects. Also, the reconstructed glimpses, so the small images corresponding to separate objects, are much smaller than the actual image. So what it means, if the model wanted to reconstruct the whole image in one go, it would have to, basically reconstruct this image in a very small glimpse and then upscale it, which would result in a very low quality reconstruction. And again, the third thing is that we have this where latent variable, which defines location but also scale. And the prior is such that it encourages small glimpses. So this prior is such that glimpse is encouraged to be small in the target, so image space. So this is that size that the smaller glimpse get pasted into the larger image, and it shouldn't occupy too much space on the larger image. So those 3 things taken together means that we want to generate as few objects as possible that should cover as little space as possible in the image. And it turns out that doing that encourages the model to decompose an image into separate objects. Does this make any sense? Say again? So just the model specification doesn't really say anything about it. But I'll show you an example where in terms of occluding objects, where the original model actually fails. And, whoops. Where the original model fails, but our extension actually does a reasonable job. Okay, so now we can proceed and talk about our extension, which is the sequential Infer repeat, which basically extends SOAIR to image sequences, right? So as a result, we learn to detect and track objects without any human supervision. We also learn motion models, which allows us to predict future motions, and we obtain a richer generative model. And I'll give you an example of this. So again, here in the top row, we have an input to the model, which contains sequences of moving 1 or 2 digits on black background, which is very simple, and we have some outputs, which are the reconstructions produced by the model with marked bounding boxes that are basically decoded from the SOAIR variable for every object. And the color of the bounding box on all future slides corresponds to an object ID. So we had some superscripts on the latent variables before, and that basically means that if the color of the bounding box on an animation does not change, that means that the model thinks that it's still the same object, which means it tracks it successfully. There will be some counterexamples as well. So generative model here, which is again like sort of the process that creates the data, is given by this diagram. It's quite a bit more complicated than the one for AIR, but you can look at it by basically having that, you know, we have 3 different time steps, t minus 1, t, and t plus 1, and at every time step, it's basically like AIR as well. But there are also some connections between time steps between them. So as in AIR, we have a separate latent variable for every object, and every frame might contain some new and old objects. So for example, in time step t, imagine that we had some latent variables at the previous time step. So here in t minus 1, and what we do, we first iterate over those variables and update them iteratively, one by one. So for example, for object number 1, we decided that like the object is still in the image and we just update its properties. For object number 3, we decided that, hey, maybe it's already left the frame and it's no longer there, so we'll just drop this latent variable, hence the gray circle. And then for the object number 4, well, we decided that J might be a new object entering the frame, so we'll introduce a latent variable. And so it continues at every time step.
For example, an object that's leaving for a new object and classify this as a new object.
So, I mean, yes, an object that is leaving. So if an object leaves and re-enters the frame, for example, right? Yeah. So yes, in that case, it can choose to forget the object, and then it will discover it as a new object, which often happens. Okay. Actually. So yeah, so this is in this particular setup, and this is because we just model whether, you know, the object exists or not. Alternatively, we could model the probability that the object is still there, and that could fix it effectively, but we haven't investigated. So inference in this model, inference is now again the process for, let's say we have a new sequence and we want to figure out what are the latent variables that describe this sequence, so basically do the object detection and tracking. So here again, the vertical axis sort of corresponds to the same time step, and we have some connections between them, right? And we have 2 phases here. The blue one corresponds to propagation, which means that we're trying to propagate or forget objects, and the pink one corresponds to discover, which is very similar to the previous model that I described at an infer repeat. So again, here we will, to infer, we'll sort of iterate over the blue objects first, and for every object we want to make a decision whether it's still present in the image or whether it left. So the first one, or the number 7 leaves and the number 8 stays. And we have arrows with different colors, and actually every arrow in this model corresponds to different RNN, so recurrent neural network, which makes it a pretty complicated beast. And once the propagation is done, we want to discover new objects in the images, and so we basically condition the process of discovering new objects on all the variables that we've already propagated. In more detail, we start with propagation, and we have the latent variables from the previous time step, so in this case t minus 1, and we iterate over them, and we also have some RNN hidden states associated with them. We have one RNN, the blue one, given by blue arrow, that sort of tries to predict the temporal change in the parameters describing this object. So we do that for the first object, and then we try to predict the latent variable for it. Here it's sort of grayed out, which means that when to forget it. And then we proceed to the next object. Again, try to predict the update in the parameters with the blue arrow. And there's also the second RNN shown in orange that tries to figure out what are the relations between objects. So for example, if objects bounce, or if there are like multiple hypotheses to sort of explain an image, this orange RNN tries to figure out which hypothesis is actually the correct one to use. And once this is done, we have the discovery stage, which is just conditions of the output of the previous stage. And it, again, looks at the image iteratively several times, and just condition propagation, but does the same thing as a Infer repeat tried to do before, which is just to look again and again and try to figure out what's new and explain this. I will skip the objective. So once you train a model, you can, for example, generate new data by sampling from a prior. So these samples were just generated from the prior distribution of the model. So we basically have some random moving digits. This basically allows you to examine what the model learned from the data. And like the only thing we care about is that, like, you know, as in the data set, appearance did not really change between time steps. Appearance of the digits and motion is sort of consistent with motion seen in the training set. What's sort of more interesting is, for example, conditional generation. So because we have this prior, we can now feed some sequence, or like a few time steps to the model, and just to condition it, and then sample like the remaining time steps from the prior. So this basically allows us to do prediction of the future, and so we can anticipate future motion even though the model wasn't really trained for this. So if you look at this again, sort of at the beginning, the motion resembles what's in the input, but later starts to differ quite a bit, and this is because we just used very noisy motion for training, so it's not deterministic, and the model cannot predict it directly. So as a consequence, for every conditioning sequence, we can do several different predictions, which will differ, in this case, because of the stochasticity in the data. They will differ quite considerably, which means the model just is actually able to capture that uncertainty. So we can compare SQAIR to the previous model, to SOAIR. And for example, we can see, like, if you see here on the left-hand side, the last two rows. So on the top of the slide, we see so this is reconstruction of different objects directly, and we see that, like, for example, on the left-hand side here, that even when objects strongly overlap for SQAIR is able to disentangle them and recover the true objects. So I'm talking about here and here, whereas SOAIR, in terms of SOAIR, heavily overlapping objects are treated as the same object. So this is a consequence of integrating temporal information, which, well, is just unavailable if you process images separately. And I think that even like in things like object detection or object classification, which is traditionally done on single images, just, you know, using temporal information can significantly improve the performance of current methods. So there was a question whether it can work on complex backgrounds, right? So no, it cannot, but here's an example where you can actually do interesting things without it. So this is data taken from static CCTV cameras on a university campus at the Duke University in the CS, in the US, and we used just common background subtraction techniques from OpenCV to subtract the background. We also inverted the colors to sort of make humans more visible, and as a consequence, what we have is unsupervised detection and tracking of walking people around university campus, which can be used for example, surveillance and behavior classification and so on. This type of representation, because now we have separate latent variables for different objects, can be very useful for downstream tasks, like, for example, reinforcement learning. And there's much more detail in the paper if you're interested. I don't really have to time to go into this right now. We can also do conditional generation. So here we have the same conditioning sequence for the 5 different sequences, and then the model sort of predicts very different outcomes for different sequences here. Again, saying that we can capture the uncertainty in the model. That's about it. I think I'll skip the future work. More about it sort of in a, also in a quite technical language on my blog, but might be some interesting details if you're interested. Code for this project is available on GitHub, and I'll take some questions right now, and you can always email me if you want to ask more. Thank you.